Cool. So again, this is the summary page for Dr. West's class. And then I will show you the summary page for Dr. West's class, and then I'll give you guys like 2 minutes or so to ask any questions you might have before we get into the actual content. As you can see, Dr. Roche is not going to be testing on 11 and 12 stuff, but Dr. West will be. So I'll be covering chapter 11 and 12 review next week. And in addition, Dr. Roche is questioning you on like pretty much all of chapter 15, whereas Dr. West is only testing you on a little bit of it. So Katrina will be going over chapter 15 for you guys next week so that there's not too much confusion or anything going on. Yeah, I always have the freaking hiccups. Hiccups. I wish I could speak. That'd be so cool. You and me both. Okay, so a couple people are still like flooding in, but that's okay. All right. Any questions, comments, concerns, anything of the sort?
I will answer the chat.
Okay, yeah, and Katrina's gonna be answering people's comments in the chat, and then if there's anything that like I should read out loud, she'll just let me know.
We're posting the file later.
Yes.
Or send an email.
It's not done.
Oh.
But my idea was we can send it out like at the end of the weekend.
Okay.
So we have time to work on it.
Okay.
So either by the end of this weekend or Monday-ish is when you'll get the file. And then I'll upload the recording to YouTube whenever it does its thing, because it takes a while. Okay, so we're going to start with chapter 13, and chapter 13 is all about conjugated systems. Yay, fun stuff. So the first thing we're going to talk about is what is conjugated versus isolated versus cumulated. So if we have a molecule like this guy we should all be familiar with. It's 1,3-butadiene. 1,3-butadiene has two double bonds that are separated by a single bond in the middle. And something we have to pay attention to is the fact that all of those carbons are sp2 hybridized. That means that we have conjugation. AKA, the electrons can go throughout the entire molecule because it's entirely sp2. And that is going to be super, super, super stable. Next up on the list is isolated. So isolated dienes are ones where you have two double bonds that are separated by more than one single bond. AKA, now it's no longer completely sp2. We have sp2, sp2, but it's separated by sp3. And if you remember from Orgo 1, you can't do resonance with sp3. So you can't have your electrons flowing throughout the whole molecule. So we call this isolated. Skipped. Okay, if you're in Roche's class, I guess he calls it skipped. Sure. And then that's meh. It's whatever. And then the least stable one is going to be this guy. So he looks pretty unstable. We don't really like that. He's going to be called cumulated because both of those double bonds are accumulated at one carbon. All of that stuff is packed and condensed, and we don't like it. It's not very stable. Any questions, comments, or concerns about this stuff? It's pretty straightforward. And if you get questions on this, it'll be like, which of the following is conjugated? And the trick there is going to be that it'll be probably in condensed formula. So You'll have to pick that, or it'll say like which one is most conjugated. And so when you're looking at a conjugated diene versus a triene or whatever, the more double bonds you have in conjugation, the more conjugated or the higher level of conjugation you have. And we'll talk about that a little bit more with UV spec. Real quick though, we're going to talk about configuration versus conformation. So configuration is what we discuss in Orgo 1, where we look at EZ or cis trans configurations. And this is when we have a double bond in the middle, and we're really trying to figure out like what the orientation of the double bond is. So in this first one, if the two priority groups are pointing opposite directions from one another, we're going to call it E, or we can call it trans. But if the two groups are pointing the same direction, we're going to call that Z, or, my bad, cis. And then the important thing here that you have to know, the trans double bond is going to be more stable because of steric hindrance. So each of those groups have more space. They're not knocking into each other. So because of sterics, trans is more stable. The other thing you have to note is that you cannot flip between E and Z / cis and trans. So you cannot go between configurations. Now, if we have conformation, that's kind of like the opposite. That's when we have two double bonds and they're separated by a single bond in the middle. So the difference really here is that you're still looking at the single bond, but you're kind of looking to see where the double bonds are pointing. And that one tends to be harder for people, so I like to just cut it in half like this. And if the two double bonds are kind of facing opposite to one another, we're going to call that S trans. And if they're pointed in the same direction, we're going to call them S cis. And so here, I don't know why it keeps going to my eraser. So here we're going to say that S trans is more stable. And that is true because of sterics again. The other thing here that you have to take note of is you can flip between conformations. And the reason you can do that is because this single bond in the middle can be rotated, so we can move something from the cis to the trans position. So, ta-da! Any questions, comments, or concerns about configuration, conformation, anything like that?
Yeah, for confirmation, when you say you flip confirmations, does that mean when would we do that to flip it? Like, why would
So,
we flip in the first place?
so you could do it for like a bunch of different reasons, and something that we learned actually, or we will be going over for the exam, is Diels-Alder, right? So for Diels-Alder, you need it to be S-cis. So let's say I gave you this. This can't react the way it is, but we can rotate this bond. And if we do that, we would get the cis double bond. Or excuse me, we would get the S-cis single bond.
All right, thank you.
You're welcome. And then we can also do it for a bunch of different like stability reasons, but we don't have to talk about that too much for this class. All right, so UV spectroscopy, all UV spec really is we are going to feed a molecule lots of energy. So we're going to hit it with lots of energy. And one electron is going to get super excited. Sorry if I keep zooming in and out. And when an electron gets excited, it's going to jump up and go to a different energy level. So we can say that the summary basically for UV spec is you hit a molecule with energy, one electron gets excited, and it jumps up one energy level. Yay. So now what's the point? So the point of UV spec is it tells you a molecule's level of conjugation. And the way it tells you that, I'm so sorry. The more conjugation we have, the lower energy we will have. That corresponds to a lower frequency and a longer wavelength. So basically what you need to know about UV spectroscopy, is that higher levels of conjugation means that something is more stable, so it'll absorb less energy. That means it has a lower frequency and a higher wavelength. So just know like how those relate to one another. So if we had this versus this, we know that the one on the right, or the one on the left, my bad. The one on the left is more conjugated, so that means it has less energy, a lower frequency, and a higher wavelength compared to this one. Any questions, comments, or concerns on UV spec? If you guys have questions, I'll wait for you guys to type them out. And while I do that, just to quickly remind ourselves, we have IR spectroscopy, which tells us about functional groups. We have NMR spectroscopy, which tells us about the carbon-hydrogen framework. We have mass spec, which tells us about the mass. And now we have UV spec, which tells us about the level of conjugation. And then someone said they didn't completely get the last part, so I assume you mean this part. So basically all I said is the more conjugated something is, so this one has 3 double bonds in conjugation, whereas this one only has 2. So that means this one has lower energy, lower frequency, and longer wavelength when compared to this one. Good, bad, meh. I'm going to assume it's at least meh. You're very welcome. Okay, so someone asked a good question, which is something that we're going to talk about next chapter, but they said, let's say we had a third double bond here, and now it's a completely different question, right? Because here we have benzene. And the big difference is that benzene is not only conjugated, it's actually aromatic. So when we are comparing an aromatic ring to a conjugated molecule that has the same number of double bonds, the aromatic one is going to be much more stable. So benzene's always going to win because being aromatic is way more stable than just being a triene. And I heard someone, yes, what's up? Oh, okay. Yeah, I heard someone unmute, but maybe that wasn't a question. So if it was a question, just let me know. If not, we're gonna move on.
So although the left structure is more conjugated, benzene always wins regardless, right? Because of what you're saying.
Well, okay, so it's not necessarily like if this one had 15 double bonds in conjugation, that would be better than benzene because that only has 3, even with the aromaticity. But if it's like 3 double bonds compared to 3 double bonds, the benzene's always going to win. Or even if it was like 4 double bonds, because benzene is super stable. But if there's like 5 or more, then you can't really tell because like then you would have to know like the exact energies. And then if there was like a lot of double bonds, then, you know, double bond would beat benzene. So it kind of depends.
Okay, thank you.
Welcome. Alrighty. So we're going to talk about molecular orbital theory, and we're specifically going to talk about conjugated compounds, and then later we're going to talk about aromatic compounds. So for conjugated compounds, let's start with the first one that both professors like, 1,3-butadiene. Wow, it's almost like we've seen this one before. All right, so I'm going to say this to you guys now, and I'm going to say it a couple more times so that nobody's like, oh, Katrina and Rose hate us. They didn't tell us stuff was going to be on the exam. It was so mean. Okay, when we're talking about molecular orbital theory, we care about the number of sp2 carbons. We don't care about all of the carbons present. So I could put 15 more carbons on this chain, and it would be exactly the same thing as 1,3-butadiene, as long as there's no other double bonds here. So if he gives you pentadiene or hexadiene or heptadiene, it doesn't matter, right? So what I'm telling you right now applies to a million carbon chain. If it's still 1,3-diene, the rules apply. And I'll talk about that again and again and again. So the biggest thing you have to know about molecular orbital theory is we are focusing on the p orbitals. So we're specifically looking at sp2 hybridized carbons. So I will just recap. sp2 is going to include double bonds, anions, cations, and radicals. Okay, so there is a difference between atomic and molecular orbitals, but for the purposes of this class, we can pretty much just say they're the same thing. That's not really true in chemistry, but for the purposes of this class, just treat them like they're pretty much the same. Okay, so in this case, the number of orbitals are literally just the number of p orbitals that you see here, right? So we have 4 and 4. And the number of pi electrons we have is also 4, because there's going to be 1 electron in each of the orbitals that are connected to a double bond. So once we have that set, we're going to move over here and we're going to draw out 4 energy levels because we have 4 orbitals. So these orbitals are going to translate into 4 orbitals in our diagram, right? And we're just going to call them pi 1, pi 2, pi 3, and pi 4. And I will say, sometimes the professors will interchange pi and psi. So those mean the exact same things. It's not a big deal, whichever one he uses. It's just a way that we count, right? So now we need to talk about something called bonding versus antibonding versus non-bonding. So I want you guys to keep in the back of your mind, the number of bonding orbitals has to equal the number of antibonding orbitals. So they kind of come in pairs, right? So we have to have the same number of bonding and the same number of antibonding. So when you have an even number, like we do here, there's 4 orbitals, we're going to draw a line down the middle just like this. Anything below the line is bonding. Anything above the line is antibonding. Right? And here, since we have 2 and 2, I know that pi 1 and pi 2 are bonding. Pi 2 and pi 3 are antibonding. And something we can use to kind of denote that something is antibonding is we put a little star here. So all the star means is antibonding. Ah,
That's like
I just meant those guys are interchangeable. That's not like the same star that we have up there. My beans. I just saw a question about non-bonding orbitals, but I think you just answered it, so we will move on. Okay, so another thing we have to talk about is something called the Homo and the Lumo. So again with the star, never mind. So the Homo is the highest occupied molecular orbital, and the Lumo is the lowest unoccupied molecular orbital. So the Homo is going to be the highest numbered orbital that's not full, but that has an electron in it. So it doesn't have to be 2 electrons in it. There has to be just at least 1. And then the LUMO is the lowest unoccupied molecular orbital. So that's the lowest number that's empty, right? And so in order to figure that out, we have to actually put our electrons in their orbitals. So when we're doing something like this, where there's only 1 orbital per energy level, we're going to go through and we have to fill up the bottom level before we can move up. So we have 1 electron, 2 electrons. Cool, now it's happy, we can move on. 1 electron, 2 electrons. Now we're done. We ran out of electrons. So we can say that the lowest number that's empty is going to be pi 3. So pi 3 is the LUMO. The highest number that has an electron in it is pi 2. So that is the HOMO. Ta-da! And this is all in the ground state. When it gets excited, the part that people kind of get mixed up is the fact that pretty much nothing is going to change when it comes to like naming and the actual orbitals. So I'm just going to copy and paste this. In the excited state, the only thing that's going to change is one of these electrons in the HOMO jumps up into the LUMO. The name doesn't change. Pi 3 is still LUMO. Pi 2 is still the HOMO. 1 and 2 are still bonding. 3 and 4 are still antibonding. The only thing that changes is the electron. And the reason we don't change the name of anything is because this is not a permanent state. It's very temporary. So this only lasts like a second, if that, and then it jumps back down to the ground state. So names don't change. And then someone asked, how come the spin is down? It doesn't matter. You won't be asked about like the spin. I just do that so you know like which one jumped up. Okay. And the last thing I'm going to tell you about this, and I did the star again. Gosh darn it. Okay, so I need you guys to know that when something gets excited, the electron jumps from HOMO to LUMO. And so if he were to ask you a question like, what's the most favorable jump of electrons or something like that, or what's the most favorable movement of electrons, it's always HOMO to LUMO, and the actual numbers depend on what molecule you have. So in this example, our electron jumped from pi 2 to pi 3. So the most energetically favorable was pi 2 to pi 3. All right, so again, if he gave you 1,3-pentadiene, he added a carbon at the end, but there's no more double bonds, no cations, anions, or radicals. It's just an sp3 carbon. All of this stays exactly the same. Nothing changes. Any questions about this so far? While you take a look at that, I'm just going to copy and paste this page because, as always, I don't give myself enough pages. And yes, the excited state is always jumping from Homo to Lumo, and the numbers, like the pi numbers, change depending on your molecule. All right, so let's look at our 3 special cases, which are the anion, the cation, and the radical. And so first we're going to take a look at the allylic cation. And I actually lied. I'm going to put this up here so I can draw things. So the allylic cation, well, first of all, that's different because now we only have 3 carbons. Uh-oh, I told you what would happen if we had more, but I didn't tell you what would happen if we had less. So when we have less carbons, we're just going to draw an orbital at each sp2 carbon. And yes, this is an sp2 carbon because it has a plus charge. So now the positive charge is empty, right? So plus means this orbital is empty. Minus means that there's 2 electrons. And a radical means that there's just 1 electron. And then we know that each carbon of the double bond has 1 electron. And I don't know why I made that such an ugly electron, but whatever. All right, so atomic orbitals, molecular orbitals, we have 3, right? So we can see 3 orbitals. And the number of pi electrons is 2, because remember we have that empty cation orbital. So now if we draw out 3 orbitals, and I'm drawing them a little bit farther apart because I want to be able to like show you things. Now when we have to figure out bonding and antibonding, it's kind of rough because we don't have an even number anymore. But we're still going to draw a line right through the middle, and whatever is below the line is bonding. Whatever is above the line is antibonding. But now we have something that's right on the line, and that guy is going to be non-bonding. So that non-bonding is essentially just a cushion that keeps bonding and antibonding equal to one another. So if you have an odd number, the one in the middle is going to be non-bonding. So in this case, pi 1 is bonding, pi 2 is non-bonding, and pi 3 has a little star because it's antibonding. So I will just put these by their respective orbitals just so it's a little bit more clear. At this point, we can go ahead and fill in our electrons. So we only have 2, and that's only enough to fill up this first energy level. So at this point, we're pretty much done. All that's left to fill in is our Homo and Lumo. The highest number that has an electron is actually pi 1, which would make pi 2 the Lumo. So now if we were to put this in the excited state, all that would happen is we move 1 electron from Homo to Lumo. Which would take 1 electron from pi 1 to pi 2 in this case. And then I will open it up to any questions while I draw the allylic radical.
I accidentally zoomed chat privately to somebody.
Oh. Are there any questions that I should answer?
Somebody said, "Can you excite something twice?"
Don't worry about that in this class. Don't worry about it. Okay, so the reason the atomic and molecular orbitals are 3 is because we're just counting the number of sp2 carbons we have, essentially. So here it would be 1, 2, 3. Yes, so in the excited state, 1 electron jumps from the HOMO to the LUMO. You are correct. All right, so this one is a radical, which means we have 1 electron here, 1 electron here, and we have 1 electron here. So I'm going to go ahead and erase the little meatball. And what's really cool is we can keep a lot of this stuff the same, because like I said, this diagram really depends a lot on, it's not going to let me do it. That's so sad. Whatever. So this diagram depends a lot on the number of sp3 carbons or sp2 carbons we have, right? So we're still going to have 3 energy levels. The top one will be antibonding, the bottom one will be bonding, the middle is non-bonding, right? And the only thing that's really changing is we're adding 1 electron. So bam. Atomic orbital is still 3, molecular orbital is still 3, but the number of pi electrons has increased by 1, and now, I'm sorry, I'm a Dumbo. Increased by 1, so now it's a total of 3. Okay, so the node configuration that they're talking about is something I drew in one of my SI sessions. Was when we have orbitals like this, we're going to have one side filled in, and then as you go up in energy level, you create a node. And what's kind of special about that is in the anion, cation, and radical, the one in the middle is going to disappear because it turns into a node. Don't worry about that too much. It's just really there for you to help, like, conceptually. If it doesn't make sense, don't worry too much about it. Yeah, they don't really test on it. All you need to know is as you go up in energy levels, you create nodes.
I mean, technically.
Okay, so someone said, if something's not conjugated, can you draw the molecular orbital? So, I mean, I guess you could, like Katrina said, like you could, I guess, but like you won't be tested on it. It's not really important. And I don't even know how it would look. It probably, to be honest.
Rosemary, when you said the AO and the MO on the left side, I'm still kind of confused about that. So the AO are the sp carbons, and the MO is just little electron thing.
So yeah, we can just think about it as, like, pretend they're the same thing, right? Atomic and molecular orbitals for this class, or pretend they're the same. And so for both of them, what you're looking for, like you said, is the number of sp2 carbons, because each of those sp2 carbons has a p orbital. So we're looking for p orbitals.
Okay, thank you.
You're very welcome.
100% the same thing.
Huh?
Somebody's asking, so for this test, we can assume AO and MO is 100% the same thing, right? They're not going to trick us.
Yeah, I mean, look, they don't test you on that. Like, they're not going to ask you, like, what's the difference between an atomic orbital and a molecular orbital. There are differences, obviously, and I'm not going to lie to you and tell you they're exactly the same thing. But for the purposes of these exams, like,
They really won't.
you know, I wouldn't spend too much time focusing on it, but I'm sure there's stuff in the PowerPoints, like, if you're super interested. But I don't want to spend too much time on that right now. What I do want to note is that in the excited state for the radical, we are going to move, again, 1 electron from HOMO to LUMO. But in this case, the HOMO is actually pi 3. So it's going to move from pi... Oh, I'm lying. Pi 2. It's been a long day. It's going to go from pi 2 to pi 3 star. So right here, the HOMO and the LUMO. Any questions about these two before we move on? And while you do whatever you do.
Why is the
Yes.
Homo pi 2 and the Lumo? Oh, I see. Never mind.
Okay. I mean, if you're wondering that, someone else is probably thinking it. So just really quick, the reason this is the HOMO is because there's one electron in it. So it's the highest number that has an electron. And then the LUMO is the lowest number that's empty. All right, so moving on. So we have the Allylic Anion, and yes, I am cheating again. Deal with it. Okay, so the anion is a negative charge. So that means there's going to be 2 electrons in here. Wow. So there's a total now of 4 pi electrons. The orbitals stay exactly the same. Everything's going to stay exactly the same. Bonding, non-bonding, antibonding. The only thing that's going to change is the electron placement. So now we're going to have bam, bam. Wow, now pi 2 is full. Yay. So pi 2 is still going to be the HOMO. Pi 3 is still going to be the LUMO. And in the excited state, we're still going from HOMO to LUMO, which in this case would be again pi 2 to pi 3. I did that one kind of fast, so if you have any questions, please let me know. But it's a lot of the same thing. Once you get the general idea, it's a lot of like, bleh, you know? You do be like that. You really, really do. Okay, so I will give you a moment. I'll zoom out so you can kind of see these guys together. Can you explain the radical? Yeah, okay. So the radical basically is the same like idea as the other ones. The only difference is now we have 3 electrons. The reason we have 3 electrons is that this guy has 1 electron in its orbital, so we have 3 total. So when we go to fill up the orbital levels, it'll be 1, 2, 3. Yeah. I forgot, I had an idea that I was going to say, but I kind of forgot it. So I guess all I'm going to say is the reason this one is HOMO and this one is LUMO is because HOMO doesn't have to be a full orbital. It's just the highest number that has at least 1 electron in it. So that's why this is the HOMO, and then this one is the first empty one. So that's why it is the LUMO. You can say which one is less stable. So the radical is going to be less stable. And the reason for that is the radical has a half-filled orbital. That sucks. We don't like that. So since it's all by itself, it doesn't have a pair, this one will be the least stable. And then between the other two, I honestly don't know. Like, I'm pretty sure it's the anion, but I could not tell you why. Any other questions? I didn't see any other ones in the chat, but were there any?
No, I just said a really stupid thing to make them remember.
Felt.
The radical's a rad dude by itself.
The way I think of it is the radical is super unstable, much like all of us. Alrighty, so for the sake of time, I'm gonna go and show you this right quick. Just kidding, maybe I won't. As long as it takes, Sarah. God. I'm just kidding. I'm just kidding. I say that, but I don't want to be here for that long, so.
It never ends from Daniel.
Daniel, you don't want to be here forever. You only have a 3-hour break. Come on.
Then what the hell?
Let's get it together, everyone. No, okay. So I didn't want to redraw this for the bajillionth time, so I'm just putting it up here for you. This is a 1-2-1-4 reaction, and I'm pretty sure almost everyone has seen it by now. So we could do another example that's slightly different, but I don't want to because this is the one that you usually see on the exam anyway. So the main concept behind this, right, is this guy, the double bond, acts like the nucleophile, which would make HBr the electrophile. And when it reacts, it adds a hydrogen to the less substituted spot. Cool, we get a carbocation. Awesome, whatever, groundbreaking. We get the 1-2 product. All right, the reason it's called the 1-2 product is not because of, like, these numbers are not IUPAC or whatever. All it's talking about is the relationship between hydrogen to bromine. So it's 1-2 because hydrogen is 1, bromine is 2. Whereas in the 1-4 product, hydrogen is right here, 2, 3, 4. Bromine's all the way over here on position 4. So that's the difference between the 1-2 and the 1-4 product. So now kinetic and thermodynamic, it's related, but it's not directly like equal. Like it's not always 1-2 is going to be kinetic and 1-4 is going to be thermodynamic. I really, 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 really need you to know that. So the kinetic product is the one that has the lowest activation energy. You can't see lowest activation energy necessarily on this mechanism, but what you can see it on is the reaction coordination diagram, which we're going to talk about. And then the way I would say, like, how do you know in this kind of reaction which one is kinetic versus thermodynamic? The kinetic one is the one that has the least number of steps and requires the least energy. How do we know which one requires less energy? It's because of the stability of this middle right here. So this cation is more stable than this cation. And this doesn't have to undergo resonance to get the product, so this one is kinetic. For molecular orbital theory, radicals are least stable because it has a half-filled orbital. The other two, I don't think you're going to have to know like which is more and less stable, but Google it.
Yeah, not for MO. I'm guessing for this because you know how you have the double bonds, the substitution of the double bonds that has another issue.
Ah,
Yeah.
to be completely honest,
No.
I didn't look into it. I'm going to be real with you. I went home that day. Everyone had COVID. And I never looked it up, if I'm being real. Chilling now. I'm live. But, yeah. I don't know. I might look into it. I probably should. If I don't, harass me over email or something. All right. But for now, we at least know that this one is di-substituted. This one is tri-substituted. So tri-substituted is for sure better, right? Doesn't matter about di-substituted. Whatever, we don't care. Tri-substituted is for sure better. So that's all we care about. And that's important because the thermodynamic product is the one that has the lowest potential energy. On the graph, I'll show you what potential energy looks like. But as far as this reaction mechanism goes, we're just gonna, yeah, I saw that question and that kind of threw off my thinking. I don't think excess HBr is going to do anything in this case because there's not really anything for it to do. And then this reaction is called the 1-2-1-4 addition. And the other thing we could call it is an electrophilic, no. Addition to addition to conjugated systems. Look, guys, my brain is on weekend mode. I'm seeing Venom in 35 minutes, so I'm not here anymore. I'm so excited. Okay. Anyway, one thing I want you guys to keep in mind is when we're talking about thermodynamic, right? They're gonna give you buzzwords like, yeah, nobody spoil the end credit scene. Now I'm distracted by the chat. Stop it, people. Stop it. Okay. Yeah, I'm gonna close the chat. Okay. So thermodynamic product, right? They're gonna say something called reversible reaction or under thermo conditions or at equilibrium. All of these things mean the same thing, right? And all of those things mean that the thermodynamic product is favored. Ahem. Another way you could say that, is that if a reaction is reversible or it's at equilibrium, that means that the most stable product is formed the fastest. Let me say again. Under reversible conditions or a reaction that is at equilibrium, the most stable product is going to be formed the fastest. Oh, but how in the world could he ask me something like that, Rose? Let me show you. Okay, sarcasm aside. Let's say he gives you something. Nope. Why do you hate me, Katrina?
No, I would send it to you. That's what I'm trying
Oh, okay, thanks.
Now that I'm trying to
She was just like, my graph is so good and yours is ugly. Okay, so if he gives you something like this, first of all, before I start drawing on it, this middle dot, right, that I just put in there, that is the starting material. Why is that the starting material? Because this isn't like an Orgo 1 reaction diagram. It's showing you two different reactions in one diagram, right? So this is going to be one reaction and you get to product A. This is going to be a second reaction, you get to product B. All right, so once you know that, you could say that this is the activation energy, this is the activation energy, and down here, these lines are the potential energies of our products. We're going to put a pin in that. We'll get to it in a second. All right, so if he gives you a graph like this, and he says, which of the following is the kinetic product? Well, you're going to say the one with the lowest activation energy is the kinetic product. The hill that's the shortest one is the kinetic. Me too, girl. Me too. Someone just yawns like who knows where. All right, now if it were to ask you something crazy like which one of these is the thermodynamic product? Well, you're looking for the lowest potential energy. Wow, the lowest potential energy is A. Wow. So this is the thermodynamic product. So what is B? B is trash. That's what it is.
B is useless.
It sucks. Okay, so if he asks you something crazy like, oh, under reversible conditions, which of the following is true? Well, we know that B isn't formed more quickly because B sucks. Yeah, and B can't sit with us either. B is not the thermodynamic. B is not the kinetic. A is the kinetic, A is the thermodynamic, but that's too easy. So theoretically, possibly, if he wanted to ask you, like, which of the following is true, right? A is going to be the most stable product. And what did we just say? Under reversible conditions, the more stable product forms the fastest. So A forms the fastest. Yay! Claps for us. Okay. While you deal with that information, how you will. No. Whoever just said 3 hills, stop it. You keep asking too many questions. You're not in Orgo 2 anymore. You're in Orgo 4. Stop. Okay. All right. So the intermediate, someone asked that a while ago, and I actually remembered your question. So the intermediate for this, we're going to pretty much say this is the intermediate. And that's why I said look at the stability of the carbocation for the intermediate, because we're going to consider this guy the intermediate / transition state. Oh, darn it. So there's no transition state in either diagram. What?
Oh, guys.
Oh, Eric raised his hand. Oh, so polite. What's up, Eric?
Why is the kinetic and the thermal on the same hill?
So the reason is because sometimes it be like that. Oh, that's a terrible answer, but basically, the kinetic and the thermodynamic product don't have to be opposites. They can be the same product.
Oh,
Yeah.
okay.
Yeah, remember? Okay, I'm gonna yell because this is okay. We're only talking about lowest. So if you look at this and you go, this is the lowest activation energy. This one is the highest activation energy. Therefore, this must be the thermodynamic. No, I will crawl through your computer screen and I will yell at you. Do not do that, please. Students get these questions wrong all the time because they do that. Lowest. Someone left. Sorry, was that too threatening for you?
Okay, there's
Failed. No, I'm kidding.
transition state saying it's not depicted in the diagram, though. Isn't the transition
The-
that middle dot?
This is the transition state, guys.
The transition state is that middle dot right there.
No.
What?
This is the activation energy is the transition state. So the activation energy is the transition state.
So if B is lower than A, it is thermo.
Yeah, if it was lower, yeah. So if we had something like
So
Yikes.
that is new chart, guys. New chart.
okay.
Let me back it up for a minute.
Okay. Hold up. I'm gonna stop recording for a second.